the Data Science Rabbit Podcast with Michael Bagelman.
In the shadowy realm where mathematics meets mythology, there exists a set of equations that can strip away the layers of fantasy to reveal something truly unsettling. The cold, unforgiving mechanics of survival. Welcome to the world of the Lotka-Volterra model, where predator and prey engage in a deadly dance choreographed by differential equations. Imagine, if you will, a world where vampires hunt humans. It's a chilling thought, but one that mathematics can help us explore with eerie precision. The Lotka-Volterra model, typically used to describe natural predator-prey relationships like wolves and deer, takes on a far more sinister tone when applied to our vampiric scenario. At its core, this model consists of two intertwined differential equations. Now, don't let the term differential equations scare you off. These are simply equations that describe how things change over time. In our case, they're describing how the populations of humans and vampires change as they interact. Let's break down these equations. The first one governs the human population, our prey. It looks something like this in words. The rate of change in the human population equals the natural growth rate of humans, minus the rate at which vampires are killing them. Now, if we were to write it out mathematically, we'd see terms for the current human population, their natural growth rate, the rate at which vampires encounter humans, and how often these encounters result in a human death. It's a balancing act between reproduction and predation, with each term pulling the population in a different direction. The second equation focuses on our predators, the vampires. In words, it says, the rate of change in the vampire population equals the rate at which vampires successfully feed and reproduce, minus their natural death rate. Mathematically, this equation includes terms for the current vampire population, how often they successfully feed on humans, which allows them to reproduce, and their natural death rate when they can't find enough humans to feed on. It's a grim calculus of survival, where every human life taken potentially creates a new vampire. These equations are coupled, meaning what happens in one directly affects the other. More vampires lead to fewer humans, which in turn leads to fewer vampires, and so on. It's this coupling that creates the fascinating and terrifying dynamics we see when we solve these equations. But understanding these equations is just the beginning. To truly grasp the horror of this scenario, we need to see it unfold over time. Enter the Runge-Kutta method, a mathematical tool that allows us to solve these complex differential equations and simulate the grim dance of predator and prey, step by chilling step. The Runge-Kutta method works by breaking time into small intervals and using the rates of change from our equations to estimate how the populations will look at the next time step. It's like taking a series of snapshots, each one showing the human population shrinking as the vampire numbers swell. Here's how it might play out. We start with initial populations for humans and vampires. The method then uses our equations to calculate how much these populations will change in the next small time interval. It does this by evaluating the equations at multiple points within this interval, combining these evaluations in a clever way to get a more accurate estimate of the change. We then update our populations based on this calculated change and move to the next time interval. This process repeats again and again, each iteration bringing us closer to the grim conclusion our equations predict. With this powerful method, we can simulate the entire nightmarish scenario. We can watch as vampires overtake humanity, see the human population crumble, and witness the vampires' own desperate fight against starvation as their food supply dwindles. The equations make it clear. It's not a question of if this apocalypse will happen, but when. Through the combination of the Lotka-Volterra model and the Runge-Kutta method, what begins as a mathematical exercise transforms into a vision of doom. Vampires and humans, trapped in an unstoppable cycle of predation and decay, march towards a bitter end governed by nothing more than cold, logical equations. In this mathematical nightmare, the predators may seem to win at first, but their victory is hollow. As the prey falls, the system itself collapses, because that's what the math demands. It's a chilling reminder that in nature and in our imaginations, the most terrifying monsters might not be the ones with fangs, but the implacable laws of mathematics that govern life death, and extinction. So the next time you find yourself pondering the supernatural, remember, sometimes the real horror lies not in the creatures of the night, but in the equations that predict their fate. And ours. The Lotka-Volterra equations and the Runge-Kutta method aren't just mathematical curiosities. They're windows into the merciless logic of survival, extinction, and the delicate balance of ecosystems, whether those ecosystems exist in nature or in our darkest fantasies. Let us hear how these models can help us understand the balance of humans and vampires in our world.
We begin our descent into darkness with the Stoker King model, a nightmarish construct inspired by the blood-curdling tales of Bram Stoker's Dracula and Stephen King's Salem's Lot. In this grim reality, vampires are relentless. They feed constantly, and every victim they drain rises as a new vampire. Their numbers swell, doubling with each sunset, and as the vampire population grows, the human population dwindles, helpless before the onslaught. The model shows us a terrifying truth. Within months, humanity would be nearly wiped out. The equations behind this chilling outcome are deceptively simple. Borrowing from the Lotka-Volterra model, the Stoker King scenario applies predator-prey dynamics with vampires as the relentless predators. Humans, the prey, dwindle to extinction as vampires multiply uncontrollably. The growth of vampires is exponential. Feeding on human blood like a virus, their numbers surge until no human remains. There's no respite here, no last-minute salvation. The numbers are cold and merciless. Within 165 days, the Earth would be a desolate place, ruled by vampires feeding upon one another, until they too face extinction. The epidemic spreads and destroys, and in this world, the predator's hunger knows no bounds. The math shows us a fate more terrifying than fiction, a fate where survival is impossible. But what if the nightmare were slower? In the dim light of the Rice model, we find no comfort, only a delay of the inevitable. Based on Anne Rice's Vampire Chronicles, this model introduces a cruel hope. Vampires feed more discreetly, they don't kill all their victims, and conversion into vampires is a rare, slow process. But make no mistake, the end is still the same. Humans might survive for decades, watching as their numbers slowly dwindle under the vampire's subtle predation. Yet, like a disease spreading through the veins of a dying host, the human race is still doomed. The clock ticks slower, but the hour of extinction is still near. Mathematically, this model offers a slight reprieve. The lethality of vampires is reduced, the conversion rate lowered, and yet the equations remain unforgiving. The human population shrinks in proportion to the growing vampire numbers. This is a Lotka-Volterra system with a darker twist. The predators, though slower, more cunning, still win. The numerical solution, calculated through the eerie precision of the Runge-Kutta method, tells us that even this quieter horror leads to the same fate, human extinction, just delayed by a few decades. The Rice model is a creeping terror, like watching a candle slowly flicker out in a darkened room. The equations show that while humanity lingers, the result is clear: collapse. There's no stability, no balance, just a slower descent into the abyss. A dwindling species, surrounded by predators that need only wait. And yet, in the third and final model, a chilling balance emerges. The Harris-Meyer-Kostova model offers something the other two do not: a fragile coexistence, one that could be easily shattered. Inspired by Twilight, True Blood, and The Historian, this model introduces new elements. Vampires can feed on alternative sources, such as animal blood or even synthetic substitutes. There are vampire slayers, shadowy figures who silently regulate the vampire population, maintaining a delicate equilibrium. Here, the mathematics grows more complex. like a web spun between predator and prey. Vampires do not feed with reckless abandon. Instead, they manage their hunger, their existence becoming more about survival than conquest. The predator-prey equations shift into something new. There is now the possibility of cyclical stability, where both vampires and humans can continue to exist without wiping one another out. But beware, this balance is tenuous. The slightest miscalculation, an increase in vampire feeding, a drop in human population growth, could send the entire system spiraling into collapse. The Harris-Meyer-Kostova model introduces hope, but it is a hollow, fragile thing. Using the Runge-Kutta method to simulate this system, we see a world in which vampires and humans fluctuate in number, rising and falling like the tide. But it is not a peaceful coexistence. It is a truce on the edge of disaster. The slightest shift could end it all. Like a glass vase teetering on the edge of a table, this model shows us a world that could shatter with the smallest of disturbances. So what do these grim mathematical visions teach us? The Lotka-Volterra equations and the methods used to solve them, methods like Runge-Kutta, may have been designed for ecosystems of wolves and deer. But here, they reveal the dark truth of any predator-prey dynamic. The numbers paint a bleak picture, one that mirrors the fragility of life itself. In the Stoker-King model, we learn that unchecked growth, like that of an invasive species, leads to inevitable collapse. No prey, no predator. The Rice model teaches us that slowing the pace of destruction does nothing to alter the final outcome. Even delayed extinction is still extinction. And the Harris-Meyer-Kostova model? It shows that balance is possible, but fleeting. One wrong move, one change in the delicate equilibrium, and everything comes crashing down. These models, while exploring the world of vampires, offer an eerie reflection of real-world ecological principles. The predator-prey relationships in these scenarios mirror what happens in nature when predators are left unchecked, or when resources are mismanaged. From the collapse of ecosystems to the devastation of invasive species, these equations tell the same story over and over. Predators must be controlled, prey must have room to recover, and without balance, both are doomed. In the end, the equations are merciless. They offer no hero, no last-minute save, no twist of fate. They simply reflect the truth. Whether in the realm of vampires or in the real world, balance is everything. And when that balance is lost, extinction is not a matter of if, but when. The equations will have the final word.
All right, buckle up, because this deep dive is going to get a little...
Oh, we're going there, are we? Vampires.
You know it. But hold on, before you hit that skip button, because we're not out here hunting creatures of the night.
Yeah.
No, we're diving into something even juicier. Mathematical models about vampires.
Okay, you've piqued my curiosity. I'm intrigued, as always.
So we've got a stack of research papers, some more serious than others, all wrestling with this question. Can vampires and humans coexist? What would that even look like? But here's the thing, and this is important. We're not trying to prove or disprove vampires exist, at least not today.
So no garlic-based experiments for this deep dive.
Not this time. Our mission today is exploring the kinds of relationships these models suggest are possible if we accept certain, let's call them ground rules, about how vampires behave.
All right, so for the sake of argument, vampires do exist. What's our first scenario?
But we got to start with the classic, right? Total vampire apocalypse.
The one we all secretly kind of sort of think about?
Exactly. And this 2008 paper by Ithimio and Gandhi, they went straight for the jugular with this question. What if every vampire bite creates another vampire? One bite, one more bloodsucker, on and on.
Doesn't sound good for us humans.
You think? These researchers weren't messing around. They went full-on math whiz and used what's called exponential growth to model it.
Exponential growth. So, like
this, imagine. One vampire, they bite someone, now there are two. Each of those bites another, now we're at 4, 8, 16, 32. It explodes.
And how long before humanity's on the ropes?
Okay, get this. As little as 2.5 years, 2.5 years, That's a barely enough time to catch up on all those vampire shows, let alone find a decent garlic farm to hide out in.
You seem oddly thrilled by this hypothetical bloodbath.
Maybe a little, but seriously, even if we never meet a vampire, the paper hits on something big. Population dynamics matter. If a few of.
Well, anything can multiply that fast. It makes you think about how fragile things are, An unchecked predation, not exactly a recipe for a balanced ecosystem.
Absolutely. It highlights how delicate the balance is, even in our own world. Although, we gotta admit, this model makes some assumptions.
Like what?
Well, it assumes all vampires operate on the same,
Yeah.
let's say, program. That they're all just bite-obsessed machines. No nuance, no strategy.
Like a mosquito that can outsmart you in a debate? Something like that. It's a starting point, sure. But things get way more interesting when we factor in more realistic elements. Different vampire behaviors, other things that affect population, and of course,
the many, many types of vampires out there. Because, surprise, it's not all capes and fangs.
yeah, turns out the world of vampires might be even more diverse than, well, the human world when you think about all the stories out there.
So we're not necessarily doomed to a vampire free-for-all.
Not necessarily. Some researchers actually asked, what if vampires are a bit more, shall we say, discerning about their dietary choices?
Okay, strategic vampires. Are we talking like I only drink ethically sourced blood kind of vampires?
Not quite, although that would be an interesting model to explore. But this 1982 paper by Hartle and Mellman, now these researchers were ahead of their time. They used something called differential equations too.
Okay, hold on. Differential equations. I'm getting some not-so-fond memories of high school math class here.
Don't worry, no need to pull out the textbooks. It's more about, imagine you're not just tracking where a vampire is, but how fast it's moving, in what direction, how those things change.
Okay, so like mapping out vampire movements on a grand scale.
You could say that they used these equations to model how vampire and human populations might grow or shrink depending on different things. And unlike that first apocalyptic scenario, these guys factored in things like, well, vampire death rates.
Makes sense. Sunlight, steaks, those garlic-loving chefs out there, it all adds up.
Exactly. It's a tough life being a vampire, potentially. But beyond how many vampires are taken out of the equation, they also included human birth rate.
Because, hey, we're not going down without a fight, right?
Right. We've got newborns to protect. But the really interesting part, they introduced this concept of optimal blood-sucking strategies.
Hold on, are you saying there's a right way and a wrong way to be a vampire, like strategically speaking?
Imagine like a vampire buffet,
Okay, now you're speaking my language.
Yeah.
Those long tables, the silver domes.
Exactly. So you've got your blood maximizers, right? All you can eat, drain every victim dry. Then there are those who are a bit more, got portion control, take what they need, try to blend
Would
in.
probably invest in some good mouthwash.
Possibly. And then, of course, you've got your eternally thirsty vampires, always wanting more no matter how much they consume.
So it's like the vampire version of different dietary philosophies. You've got your foodies, your mindful eaters, and then those who just can't resist a second helping or a third or.
Precisely. And while this might seem a little silly, the idea of optimizing resource consumption, that's huge. It's relevant to us, even if we're not dealing with, blood. It's how we manage forests, fisheries, even how much water we use.
So from mathematical vampires to real-world resource management, I'm sensing a connection here.
Absolutely. These models, even the ones about fictional beings, they can give us this new perspective on the systems that, they kind of run our world.
Mind blown. But okay, those first two models were either going extinct or living in a constant state of, are they going to bite me?
Yeah.
Anxiety. What about a model based on a more modern take on vampires? You're saying there's hope, even if these creatures of the night walk among us.
Well, a 2013 paper by Strielkowski, Lisson, and Welkins, they decided to explore that very question. But get this, they based their model on vampire fiction.
Wait, hold up. They used vampire novels and movies as their data, like actual stories.
You heard that right. We're talking Bram Stoker, Anne Rice even dipped their toes into Twilight and True Blood.
Okay, this is amazing. This paper's like a gold mine for anyone who loves their vampires with a side of math. We'll definitely link to it in the show notes.
And what they found is pretty interesting. While some scenarios, like that rapid spread of vampires in Dracula, that still led to, let's call it a population downturn.
Right, not ideal for us humans.
But other fictional worlds, they painted a more balanced picture, you could say.
So, which vampire stories give us a fighting chance? What's the secret to survival?
Well, the models based on more restrained vampires, especially the ones with, shall we say, alternative food sources, those showed a real possibility of long-term coexistence.
So less humans are the only entree, and more. What? Vegetarian vampires.
You're not exactly vegetarian, but you're getting the idea. One model they looked at, they called it the Harris-Meyer-Kostova model.
Catch you.
Right. And in this model, vampires, they either go for animal blood or even rely on those synthetic substitutes like they do in True Blood.
Clever vampires. But how does that change things, big picture?
Well, it throws a wrench into that whole vampires need human blood to survive thing, right? And here's the kicker. When you combine that with, let's say, a limited number of effective vampire slayers.
Limited? Are we saying Buffy dropped the ball?
Not necessarily Buffy, but in this model, slayers, they're out there, but maybe these vampires are just really good at, not being found.
Masters of disguise, PR teams.
Exactly. Point is, it's not a free-for-all for slayers. And what happens? You get a surprisingly stable system.
Stable how?
Well, instead of that inevitable march towards extinction, it's more like, those cyclical predator-prey relationships we see in nature, like wolves and deer, they keep each other in check.
So, less apocalypse, more like a weird vampire-human ecosystem that we're just all managing.
It's a fascinating thought, isn't it?
It really is. Okay, so we haven't found any real vampires yet, at least none that have come out of the coffin, so to speak. But what we've learned today is that these models, even ones about the fictional, they can teach us so much about our own world,
Absolutely. And they remind us that the assumptions we start with, they matter. Mindless bloodsuckers. Yeah, we're probably doomed. But strategic, discerning, maybe even a little picky about their beverages, hey, there might just be a way for everyone to, share the planet.
It's like that old saying, assumptions are the vampires of logic. Did I just make that up?
I believe you did, but it's quite fitting.
Right. On that note, we'll leave you to ponder this. What other hidden dynamics, unexpected connections might be shaping the world around us? Food for thought from the Deep Dive. We'll catch you next time.
If you are interested in the documents used for this podcast, here they are. The first document is titled Mathematics of the Human-Vampire Conflict by Dino Sejdinovich, published in 2008. This article explores mathematical models of vampire-human interactions, analyzing whether vampires could theoretically exist based on population dynamics. It critiques previous mathematical arguments against vampire existence and proposes more sophisticated models that could potentially allow for vampire-human coexistence under certain conditions. The second document is a research paper titled Mathematical Models of Interactions Between Species: Peaceful Coexistence of Vampires and Humans based on the models derived from fiction literature and films by Wadim Strelkowski, Evgeny Lissin, and Emily Welkins, published in 2013. This academic paper provides a detailed mathematical analysis of vampire-human population dynamics using differential equations. It examines 3 models based on different vampire mythologies from popular culture and evaluates the conditions under which peaceful coexistence might be possible. The third document is a set of presentation slides titled Mathematical Models of Interactions Between Species: Peaceful Coexistence of Vampires and Humans by Julia Inozemtseva, likely from 2013 or 2014, based on the source material being the previously mentioned paper. These slides outline various mathematical models of vampire-human population dynamics, including the Stoker-King model, the Rice model, and the Harris-Meyer-Kostova model. The presentation examines how different assumptions about vampire behavior from popular fiction affect the possibility of long-term coexistence between vampires and humans.
This has been the Data Science Rabbit Podcast, hosted by Michael Bagelman. Find the Data Science Rabbit Podcast on all your favorite social media, including YouTube and TikTok. Follow Michael on LinkedIn or visit datasciencerabbithole.com.